the midterm, and I have given you one break the last Tuesday. That after the midterm you had a hectic journey, so that is why I decided to give some rest to you on the last Tuesday. But from today, we'll start our regular classes, and though I will not continue two classes today, one class I will take. So actually, in Friday we have two consecutive classes, right? So for today I will take one. And in the morning session, I have found that many students have not joined yet. So hopefully from the next week, everyone will be regular. And in your class, I can see that around 16 students have joined. Okay, should I start now, or I should start from 2:30? Because 3 minutes left for 2:30, because some of you may join after that. Okay, let's wait for 3 minutes at least.
Sure, sir.
Okay. How is your midterm exam for this course? Was it okay?
Yes, sir. Alhamdulillah.
Fine. So the topic today will start after the midterm. That is the one, you can say one bus, that is the control area network bus. Or you can say that we learn about control area network bus and control area network protocol. And this is a bus technique, or this is a protocol that is specifically designed for embedded systems, likewise the vehicles, likewise the automotive vehicles. For large scale embedded system, this control area network bus has been used, and today we will see that where control area network bus is used and how it is designed. So as our course has the embedded system part, so from that point of view, I have included this in your syllabus. So let's start the recording first. Now, the control area network bus, you can say that controller area network bus or control area network bus, whatever you say, is an important embedded protocol for vehicle bus standard. And this protocol, in this bus protocol, there is multiple of devices, and of course there will be microcontrollers and devices, and those needs to be communicate with each other. They need to exchange their data for the perfect operation of a vehicle. But of course there is no host computer, rather we have the microprocessor or microcontroller to operate this, to interact with these devices. So primarily the control area network bus was designed for automotive vehicles, but nowadays these protocol or these bus techniques is used for aerospace, maritime and industrial automation, and for medical image or medical equipments. So you see that the area, the example of the area it is covered, most of those things are very large scale. So even one automotive vehicle is a large scale embedded system, aerospace, maritime, industrial automation and medical equipments. The very early controller area network bus, the world has been started in 1983, and though it is commercialized in 1987 by Intel and Philips. Okay, so control area network, as you already have that information that this protocol works with a network, and in this network, what components or what devices we have? We have the sensors, we may have the actuators, and some control devices. I will show you some example of these control devices in coming slides. And these devices are not connected directly to the bus, rather through a host processor or through some microcontroller and a CAN controller or control area network controller. These devices are interconnected and through the control area network bus. And as you know that as we are dealing with a embedded network or embedded system network, we have to specify some step-by-step rules or step-by-step procedure, step-by-step rules, that is called the protocol. That is why sometimes we say CAN protocol. This is the protocol so that the sensors, actuators, and other control devices can interact or can communicate with each other. As you know that for our internet we use the TCP/IP protocol, and it comprises with 5 layers. Actually 5 layers means these are the 5 layers through 5 layers of operation where we define the step-by-step rules. Likewise, we have the say we have the wireless sensor networks, and that has a protocol of ZigBee. Or nowadays you can say we have the IoT, and that has a protocol of LoRa. So these protocols and these networks and their corresponding protocols have some specific step-by-step rules, and those are defined through layers. Similar to that, control area network that specifies its step-by-step rules using 3 layers. One is physical layer, one is protocol layer, and another is message filtering layer. So in a simple way, what I can say that as you have already been studied the TCP/IP protocol, there you have the physical layer activity. Similar to that, we have the physical layer activity here. In TCP/IP, you have the data link layer activity. Similar to that, the data link layer activity can be mapped with the protocol layer. And we have the message filtering layer that is related to the almost network layer, because in the network layer we specify any host or any device based on the IP address or internet protocol address. Similar to that, in CAN we have the message filtering layer, and these messages can be filtered based on the identifier or ID of each of the components of sensors, actuators, and control devices. In addition, some important notes about CAN is that it ensures some priority among the devices or among the control devices. And we have some other challenging issues. In course of this lecture, you will see those challenging issues. So let's have some brief idea about the development of CAN, though it's theoretical, but I'm telling it in a summarized way. Actually, the development of CAN was first introduced for modern motor vehicles, where more and more electronic devices were implemented. And what kind of functionalities or management systems are incorporated in modern motor vehicles? You can see that we have the engine management system, we have the active suspension, automatic brake system, gear control, lighting control, air conditioning, airbags, central locking. So everything is controlled, or everything is needed to be controlled in the modern motor vehicles. And why do we need that? For the safety and more comfortness of the driver as well as for the passengers. And another thing is that, of course, our main target is to reduce the fuel consumption and reduce the emissions. And that is why the overall control system of the automotive vehicles use some sensors, and these sensors need to be exchanged their information. These systems need to be supposed to know the reservation status. We use some sensors. to know the temperature of the, for controlling the air conditioning, we have some sensors to measure the temperature of the inside situation or outside environment of the vehicle. We use some sensors and they need to exchange the data. And for that reason, we use the CAN bus or CAN protocol. Here is one example of a caterpillar. You can see that the caterpillar model number 797. You have seen this sort of caterpillar in every construction sites. But in this simple caterpillar, multiple tasks can be done. Use multiple people's tasks can be done in a very easier way. But who makes the things very easier? Some sort of sensors. In this model, around more than 195 sensors and actuators is used, and they use sometimes in some cases they use the wireless data link, and they use the control area network bus or CAN bus. This is an example, but if I draw another thing is that the example I have given you about the motor vehicles, that in a motor vehicles we have these components, these functionalities. To engine control we use some sensors, for anti-lock brakes we use some sensors, and transmission control, active suspension, for these functionalities we use some sensors or actuators. On the other hand, for lighting, air conditioning, power locks, airbag, power windows, power seats, these are also controlled by the status of these functions are measured through some sensors. So everything need to be connected with the dashboard, so that from the dashboard the users or the driver can see the status of the vehicle. So in that sense, we use the embedded system, and this embedded system has these functionalities. Now, if we consider the functionalities as nodes, so this is one node, this is another node, this is another node, and these are the nodes or components in an embedded device. So let's say we have n nodes in an embedded system. Now, if every device needs to be, or every node needs to interact with each other, in that case, we need about n into n minus 1 divided by 2 numbers of links or connectivity, actually, which is very, very complex, design. From the designer's point of view, before the midterm, I have given you some brief introduction about the embedded system, where the designer's view I have shown you in one of my lecture slide. How the complexity can be measured? So let's see. So let's say we have 4 components or 4 nodes. So let's say A, B, C, D. In that case, we need 4 into 3 divided by 2, total 6 links. So 1, first, second, third, fourth, fifth, and sixth. So 1, 2, 3, 4, 5, and 6. So in this, it is a fully connected network from the graph theoretical approach. This is a fully connected network, and the number of links is 6. Now, the problem of this design is that if you increase a single node, in that case, the number of links increase exponentially, or sometimes not exponentially, drastically it increases. How that's, let's say, if we include 5, n equals to 5, in that case, 5 into 4 divided by 2 is 10. So 10 links you need to design, or you need to incorporate in your system. So this is not a flexible design concept. This is not an optimal design concept. So that is why the researchers has introduced the before CAN the embedded systems was designed in this way, but this is a complex design system. So that is why the designers have designed the CAN protocol in this manner. What they included with the components or with the functions, they included one CAN option. So this what this CAN options is holding. This CAN option is holding one microcontroller, one CAN controller, and one transceiver. I will show you in coming slides. But the main thing is that this design concept, where you can see with the dashboard, we have a high speed bus and in the opposite direction, we have a low speed bus. Why it is a high speed? Because these functionalities demands more data rate to send the data towards the data bus or to exchange the data in between them. It requires high speed data rate. In compared to that, these functionalities like air conditioning, lighting, power seats, these functionalities requires low speed data exchange rate. So that is why here as well we have a bus. So you know that what is a bus? Bus is a common place or common corridor through which the nodes can exchange the data, and bus is a collection of wires. So in compared to the point-to-point wiring, the point-to-point wiring of the previous slide before the CAN was introduced, in compared to the point-to-point wiring, this is solely replaced by a single bus system where multiple nodes can be connected, and the design is scalable in a sense that how it is scalable, because you can incorporate more functionalities with the bus, you can connect with the more things. So while you purchase one car, afterwards you can decorate with more components. You can include what they are doing. They are connecting the new decorative items. If it is an electric item, that can be connected through this bus. So this is how the system can be scaled up, or you can reduce some of the components, no problem, but there will be no change in the basic backbone of communication structure between the functions or between the components. I guess you have got the basic point of the why do we need CAN bus in an automotive vehicle, and how it is from which point of view the designers have motivated to design the CAN bus. Okay, so let's see some CAN bus overview or some features of CAN bus. Most of the examples will be based on the automotive vehicle, as because preliminary or primarily the CAN bus was designed for automotive vehicles. So first of all, CAN is called as a broadcast type of bus. Why it is called as a broadcast type of bus? As because we have a common corridor, that is the bus, and we may connect multiple components, let's say A, B, C, and D. And I guess you have the data communication course, from where you have learned that if in a common bus, if any node sends any signal, let's say A sends a signal to B, that can be transferred, or that is available to each of the other nodes. To each of the other nodes, those are sharing a common medium. So in that sense, this is a broadcast type of bus. So this means that all nodes can hear all transmissions, and there is no way to send a message to just a specific node. But how then these nodes will understand that A is sending the data to B? That is the purpose of the message filtering layer that already I have mentioned in my earlier slides. That we have a message filtering layer. With the operation of the message filtering layer, one specific node can identify that this message or this signal is destined for me. But the what point I am focusing here, that CAN is called as a broadcast type of bus, and in the we have the in the CAN hardware, it provides the local filtering through the filtering layer, so that each node may react only on the interesting message. Interesting message means that the message that is targeted towards a particular node. Let's say A is sending some signal to B, so only B will receive that, and through the help of message filtering layer, C and D will discard those, though the signal will be available to C and D as well. This is one point. And as it is a broadcast type of bus, so there is a challenge. There is a challenge that, let's say, two nodes cannot send data at the same time. Two nodes cannot send data simultaneously, as because we have a common bus. So what happens? So let's say A is sending the signal to B. At the same time, if C likes to send any signal to D, it is not possible. And you know that you have already studied the CSMA, carrier sense multiple access, with collision detection or collision avoidance. These techniques you have studied. We have the CSMA CD, and CSMA CD is specifically designed for wired communication. This protocol, or this CSMA CD protocol, is designed for wired communication, and CAN bus has taken that advantage of using CSMA CD, carrier sense multiple access with collision avoidance. But there is some arbitration technique that is incorporated with the carrier sense multiple access with collision detection technique. In coming slides, I will show you. That means what I am focusing here, that two nodes cannot send data at the same time in CAN bus, as it is a broadcast type of bus. Here is another example, that the example is that automatic brake system or engine management system of the vehicle, and ABS is treated as node A and EMS is treated as node N. And if A likes to communicate with N, and they can communicate, but the signal will be available throughout the bus. And if there is other nodes, let's say C, let's say D, and those data will be available to C and D as well, but they will discard with the help of the message filtering layer. And some basic concept, that we have a multi-master concept. I will discuss those things. The number of nodes not limited by the protocol, as because the CAN bus can allow multiple number of nodes as it is scalable. No node addressing message identifier specifies the contents and priority, and it is very easy and simple as in compared to point-to-point communication or point-to-point connection. And it has the broadcast, or you can say in some cases multicast is a special type of broadcast, you can say. So it has the broadcast or multicast capability. Let's move forward. This is a basic configuration I'm talking about. We have the ABS, that is the automatic braking system, that is considered as node A. We have the engine management system, that is node N. Now, this is the system of the car or automotive vehicles. But what needs to be incorporated with this, we need to incorporate our host controller. This host controller is the microcontroller, and this microcontroller is connected with the ABS, and thereupon we have the CAN controller, which actually which has a driver software of CAN protocol. The software or the CAN protocol is need to be installed or loaded in CAN controller. And also there should be a transceiver that will transmit and receive the signal to and from the bus. And you see this is the transmitter that sends the signal to and from to the bus. And similar to the EMS, it has a microcontroller. We have the CAN controller and we have the transceiver. Another thing is that the CAN bus has a resistance of 120 ohm, and the signals are digital signal in a serial bit stream. The digital signals can be exchanged between the nodes, then with a high signal and low signal, two status with a high signal and low signal. And the maximum length, the optimal length of the CAN bus, you can say that is 40 meter or 130 feet, where we can achieve a maximum speed of 1 Mbps, the maximum data rate, exchange rate of 1 Mbps. So within a limit of 40 meter or 130 feet, a 1 Mbps data rate can be exchanged. That means, let's say this is our bus, and here we have the node A, and here we have the node B, and the distance between node A and node B should be optimally, it should be 40 meter so that they can achieve 1 Mbps of data rate. Now, is it not possible to, if the question you may ask that, is it not possible to have the more than that, the distance? Yes, it is possible. It is possible, but what will happen in that case? The distance will be increased, and for a signal, there is an attenuation problem. With the increment of the distance, with the increase of the distance, the signal gets weak, and this is called the attenuation problem. So that is also applicable for this copper wire, as we are using the copper wire, and through these copper wires, the electromagnetic signals are exchanged between the components. So optimally, the optimal distance is 40 meter. I can show you the another graph. Let's talk about the graph first. Okay, I'll show you the graph. This is the graph. This is the bus transmission speed, how they have measured the bus transmission speed. You can see the bus length, they have increased at the x-axis from 0 to 10, 40, 100, 20, 1000, 10,000 meter. And in the y-axis, we have the 5 kbps, 10 kbps, 1000 kbps, up 1000 kbps is the 1 Mbps. Okay, you can see that at the range of 40 meter, we have an optimal data rate of 1000 bit rate, or 1000 kbps. So that means 1 Mbps. And after that, if we increase the bus length, the data rate drastically decreases. You can see. So from there, the designers have ensured that the optimal bus length should be, maximum bus length should be 40 meter. Within 40 meter, the nodes can exchange the data and at a high speed of 1 Mbps. So this is the thing, and the rest of the things I will discuss in the next class. Okay. Another thing is that electromagnetic interference, as you know that in a typical computer system or in a typical embedded system, apart from the CAN bus, there might be some other connections like power connections, some other communication, some other CAN bus as well. So they might make some additional signals. Those may interfere this targeted CAN bus. So that is called electromagnetic interference, and that is why this arrow sign is through this arrow sign they have made us understood that electromagnetic interference is applicable for CAN bus. And you see that to reduce the sensitivity of the electromagnetic interference, even more, the bus lines can additionally be shielded. You can see that we may have an option of shielded, and you already been familiar with twisted pair cable maybe. The twisted pair has two options. One is unshielded twisted pair, that is called UTP, and another is shielded twisted pair, that is the STP. What is the difference? The difference in terms of cost, UTP is less expensive and STP or shielded twisted pair is a bit expensive. But what is the main advantage of shielded twisted pair? It is less prone to the interference. But UTP is more prone to the interference. So that is the difference. And of course, there is also the option is there that the CAN bus can be molded with the shielded coating. So CAN is insensitive to electromagnetic interference if you use the shield. Otherwise, it is prone to the interference. This is all about as a whole. I have completed up to this slide in our section 2's class today, and I don't like to extend more for today. After the midterm, after a long break, we have started. So just I have given you one brief idea about the CAN introduction. Why do we need CAN, and for what purpose we should use the CAN bus, and what is the basic features of CAN I have discussed today. And hopefully in the next class, I will talk about the operation of CAN, the protocol operation of the CAN in the next class. So from this slide, I will start in the next class on next Tuesday. If you have any question, then you can ask me. Anyone has any questions? Oh, okay. So your number of participants are good, around 22. They were in the morning only 27. Maybe due to winter, in the morning they missed, some of them missed the class. Anybody have any question? Okay. If no, then I like to finish the class for today, and hopefully we'll see in the next Tuesday, and from next Tuesday we'll have our regular labs as well online. So thank you. And Allah Hafiz.